Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and today we have a duet, and I'm very happy to have Justin Linford and Elias Aydi. Hi there.
Thank you. Hi.
Hello.
Elias, where are you located at?
I'm in Michigan. Currently, I'm a postdoc at Michigan State University. So I'm located in East Lansing, Michigan.
Is there still snow on the ground in
everywhere?
Yes.
Everywhere. Yeah, definitely.
And Justin, where are you located at?
I am at the National Radio Astronomy Observatory, New Mexico office in Socorro, New Mexico.
And is there snow on the ground
there is in the spots that are always in the shadow. We had a snowstorm like a week ago, and you can occasionally find very small clumps of it, but it's not like in Michigan.
Yeah, I think Michigan's gonna win because there certainly isn't any of it in Phoenix. No, it did get a little chilly the other day, a couple days ago, but we didn't get any snow. So very cool.
Right.
Nice. And Elias, what do you like to do for research?
So most of my research focuses on classical novae and optical transients in general. I do multi-wavelength observations of novae, and also I dabble in hydrodynamic simulations of evolved stars. Nice. So yeah.
Very nice. And Justin, where do your research interests take you?
I like things that explode. So basically anything that blows up in space, I'm keen to look at it with, at least with radio telescopes.
Which is going to be absolutely perfect. Head into this very lovely APJ supplement article, Classical Novae at Radio Wavelengths. Justin, Elias, take us away.
Cool. So I'm going to start with just a brief introduction about why we are interested in studying novae at radio wavelengths and other wavelengths. And particularly in the past decade, the interest in these eruptive events has been revived, particularly with the detection of GeV gamma rays, the highest energy light from these events using the LAT telescope on Fermi satellites, so the NASA gamma ray satellite. And since 2010, Fermi has been detecting routinely novae in gamma rays. We have around 18 now that have been detected, and this detection highlights the role of strong shocks that are taking place during the eruption. Likely due to the interaction of multiple phases of mass loss, where these ejecta are slamming into each other and leading to shocks which are accelerating particles to relativistic speeds and emitting gamma rays. And the presence of this high energy gamma ray emission in novae has somehow altered our understanding of these eruptions and has opened up the field into completely new physics and also new interpretation of the multi-wavelength emission that we receive from novae. Recently, our group has led multiple efforts on trying to understand the role of shocks in powering novae. And we found that shocks could indeed power a substantial fraction of the volumetric luminosity of the nova, even maybe exceeding that emitted by the thermonuclear emission on the white dwarf surface, which were thought as the main producer of the optical light in these events since they were discovered. And our group studied novae in all type of wavelengths, and of course including radio. And this paper was a big collection of radio observations of a large sample of novae to better understand novae in the radio wavelengths. And I think that's Justin now can give us a more detailed idea about the radio observations that have been sampled in this paper.
Cool.
Nice. I hope I can. So real quick, a big shout out to all of our co-authors, this in particular, Loa Tomek, the first author on this paper, who unfortunately couldn't be with us to do this chat. But this was a huge collaborative effort over several years involving, professors, graduate students, postdocs, research scientists, everybody, everything in between. So this is a huge effort, and it was a lot of fun to work on. Actually, I really enjoy working with our group.
International effort, one might add. Look at those.
Yes, that is true. So most of the data that we're going to be looking at today was taken with the Very Large Array, which is a radio interferometer located in New Mexico. 27 individual antennas that can go through separate stages of configurations, is what we call them. So we can have all the antennas kind of close together in what we call D configuration, and then we spread them out a little bit further and a little bit further. And when they're the most separated, that's what we call the A configuration. And that's when we get the highest possible angular resolution.
Yes.
And so throughout this paper, sometimes you'll see things called out like during A config, things looked this way. And that's our way of saying when we had the highest spatial resolution, we were able to tease out these details. Okay. So just a quick thing in case you're not used to BLA jargon.
Right. Jargon note, very good.
So let's see. First of all, with the figure 1 there, that's just on page 2, I believe. Another thing that I should point out is that a good fraction of this data, or these data, were archival. So these were done, I think the first set of observations were from like 1967. And you get up to then, just like a couple years ago. So the research in the data in this spans like 50 years worth of data collection. Nice. Some of it was taken from previous publications. Some of it was recalibrated and reanalyzed ourselves, sometimes with help of undergraduate students, sometimes graduate students. So there's a big variety in both data quality and data quantity as we step through this. But one thing to notice straight off with this first figure is on the top rows in the black there, you have the visual or optical light curves of these novae. And then in the colored points underneath, you have the radio observations at different frequencies. And straight off in just this first figure comparing 4 separate novae, you can see there's a huge difference in behavior between novae, right? That HR del has all kinds of freaky peaks halfway through
right
eruption.
Right.
Whereas V1500 SIG is basically just kind of straight line down.
Yep.
We see similar range in behavior in our optical wave or our radio observations as well. These early ones, sometimes in the early days of studying novae with radio instruments, you didn't necessarily get on them early because, as you'll see, like especially with that V351 pup, you can see it takes a long time for some of these novae to get bright in the radio. So early on, people didn't even bother looking at them until 50, 60 days after you first spotted it in the optical.
Right.
But as you'll see, as we get further into the paper, there's some really interesting stuff that you actually miss if you don't get on it early.
Yes.
Which is exciting.
Yes. Yes. Nice to see the curves have some clean separation here for.
Right. So what you see, especially with that V351 pup, that's kind of our typical quote unquote. You're going to find out the more you deal with novae, the more you understand there's no such thing as a typical nova. So with V351 pup there, you can see that what we call the typical behavior in the radio wavelengths of a classical nova, right? It starts out with its brightest at the higher frequencies. It kind of gradually increases in brightness. It reaches some peak, and then it starts getting dimmer. the high frequencies typically get dimmer first as it gets optically thin at the higher frequencies first, and the photosphere recedes back through. And then everything kind of ends up all optically thin at roughly the same flux density. And you just kind of go out with all the dots there on the right-hand side, just kind of lining up on top of each other. So the idea behind that is the theory, the simplistic theory, is that you have, right, these novae have are material building up on the surface of a white dwarf until you trigger thermonuclear reaction. So all of a sudden you get fusion going on. That it's not technically an explosion, if I remember the term correctly. It's actually a conflagration, because the velocities aren't fast enough to be technically an explosion. But you get to say the cool word conflagration, which is
there we go. There we go. I like that.
So that throws all this material off the surface of the white dwarf that had been building up on there from the companion star. The theory in the radio is that all this stuff is getting hot and it's emitting via free emission. So all these electrons are moving around and, you know, accelerating past each other, and you get free emission. And initially, it's all optically thick. And so you're seeing stuff at the very edge of this expanding material. And because it's thermal, that has a certain spectral index, and the higher frequencies are brighter. As you get bigger and bigger, everything cools down, and then it starts getting optically thin, but it gets optically thin at the higher frequencies first. So that photosphere starts receding back through at the higher frequencies, and then that's how we kind of, at the end, you pile up where the photosphere is all in one place at every frequency as it gets dimmer.
Cool. I'm with you.
Okay. All right, so that's kind of what you're seeing there in B351 PUP. So keep that in mind as like your quote unquote typical radio light curve.
Although we know there isn't any.
Exactly.
Okay.
If I may say something regarding this particular plot. So Justin mentioned the optical light curves at the top, and we're going to see that in several examples. We can see that they are all different, and like we have different type of behavior in the optical light curve of Novae, which still many of which we don't understand particularly well, and why we have like these flares. Or now we have some theories to try to explain some of them, and supported by observations. For example, the dip we see in FH Sur at around like 100 days, this is caused by an episode of dust formation. So we have dust condensating in the Ejecta. We still don't understand how dust actually condensate, but we know that dust is blocking a fraction of the optical light. So if we look, for example, in the infrared light, we'll see an excess. So we see an increase in the emission. So the optical light curve with dips, and the infrared light curve would usually like show a bump in it, or at least like stay constant. And this is, for example, due to dust formation. But what is really, I think, interesting and like need to be noted is this shout out to the citizen scientists that usually provide us with this kind of data set. So all the optical light curves presented here are actually taken from AUVSO databases, and they are actually taken by citizen scientists. And because Novae are bright and they are in our galactic backyard, citizen scientists usually do an amazing job in following up on these eruptive events. And they have now the capabilities to provide us with broadband photometry. So almost every galactic nova is followed up in BVRI, sometimes even in like other bands when possible. And these data sets are really very valuable to us.
Very nice. Cool. Thanks. Very cool.
Thanks for pointing that out, Elias. I neglected to mention that.
That's why duets are good.
Yep, exactly.
Yeah, where shall we go from here?
I think let's move on down. I don't think we need to focus too much on the tables through this.
No, but we do have some nice tables here of the ones observed.
Lots of information, and there's even more information available online in machine readable format. So anybody who wants to play with this data and do their own analysis, please help yourself. Have fun.
I can maybe mention just a couple of words about the table that we, not this one, the one on the table.
Table one.
Table one.
Table
so
one.
yeah, so in table one we'll list a lot of parameters about the novae and their optical properties. And here we have, of course, the position of every nova, when they were discovered, and as Justin mentioned, the nova sample goes from 1967 all the way to 2018. So it's a really nice sample through several decades. And then we try to characterize some of the parameters like the peak, how fast the light curve has been declining in the optical, how much extinction are towards the nova, and in order to derive maybe distance to the nova and then get an idea about the brightness, temperature, and everything. But in order to derive these distances, we actually rely on either information from the literature or Gaia parallaxes, or what is the majority of these distances are actually taken from galactic dust maps. So what we do is we use the optical spectra and some dust tracers like sodium D line or diffuse interstellar bands, and we try to measure their equivalent widths and use some pericorrelations to get an idea about the extinction toward the nova. And once we have an idea about the extinction, we try to place the nova in a galactic dust map and try to get an idea about its distance. And this is where most of our distance come from. So several distances, especially for the later, like the earlier novae, which are from 2012 onwards, maybe 2010 onwards, so past decade, we have good high resolution spectroscopy for them, so we can measure their extinction, the extinction towards them, and then get an idea about the distance. The other parameters that are, I think, also important to get an idea about the expansion velocities of the ejecta is this V1 and V2. We think that novae have at least 2 episodes of mass ejection, a first initial slow one followed by a faster one. This is where we think the shocks are happening. And here are measurements of the first, like the velocity of the first flow and then the second flow or the faster wind. And this is also done from early high resolution optical spectroscopy that either we have obtained or we found in the literature. You can see that for the first one, there's a lot of question marks because in order to get the velocity of the slow flow, we need to get on the nova before maybe it peaks. And this could be like a day or 2. And now we are very good at doing this, but maybe 30 years ago, people were not that interested in getting on nova that quickly. So you can see like the more recent one, now like if a nova is discovered, we try to get on it same night. Or
sure.
I think it's also interesting to look at the range in those velocities as well. I mean, the slow velocities can be, 800 to, or even less than 800 up to, a couple thousand, maybe 3,000 kilometers per second. Where some of those fast velocities, you're looking closer to 5,000 kilometers per second, which is fast, but keep in mind, it's also not relativistic, right? So that's something that that was surprising when novae were first seen with to emit gamma rays. Everybody was very surprised. You're not supposed to get particles up to relativistic velocities.
Oh, yes.
To make gamma rays when they're moving at 5,000 kilometers per second or slower. So.
Right. At least through a collision.
Right.
Very good. Cool. Okay, so onward from the table 1.
Table 2 kind of shows you a quick summary of the different novae and whether it's been worked on before or whether we've worked on it ourselves.
Wow.
Whether other people are working on it.
Wow. Okay. Very good. This project's been going for a while.
Yeah. We usually follow up on Novae in the radio for a few years.
At least, yeah.
Okay.
So figure 2 gives a little little bit more feeling for how varied the light curves for novae can be. And also how that the optical light curve doesn't necessarily tell you what the behavior in the radio is going to be. If you look at V1723 Aquila at the upper right there, I mean, the optical just kind of, falls off, gets dim kind of fast, doesn't do anything super exciting. Whereas the radio went on for 1,000 days. It's bounced around, it did some weird stuff. So yeah. Unfortunately, if I remember right, 1723 Aquila wasn't particularly well followed. You can see how sparse the optical light curve is.
Yeah, doesn't have the density of light.
Yeah. But it might be one of those super rare cases where there's actually more data points in the radio light curve than the optical light curve.
Okay.
Which doesn't happen very often.
Fair enough. Very good. Very good. But quite just a diversity of
observations.
Yes. You can also see with the V1723 Aquila radio light curve there, it doesn't look anything like that first one that I told you what a radio light curve should look like for a nova,
yeah,
right?
Going back to our typical example.
Yeah, yeah. So a kind of T-Pix looks typical-ish, although anybody who catches me saying typical and T-Pix in the same sentence is going to be extremely angry at me because T-Pix is a weirdo in every sense of the word. Yes. But you can still see the radio light curve at least looks moderately normal, where it gets brighter, it turns over. Whereas 1723 Aquila, it gets bright, it gets very bright at the low frequencies in particular, bumps up those black dots there. So like around 5 gigahertz, gets bright pretty quick, and then it settles down, and then it gets kind of bright again. Right. This is what we would call a double peaked radio light curve. Okay. And we'll get into some excitement, some of the exciting aspects of that a little bit later as we go down.
Okay, good. Where should we go next?
I think probably down to the next figure is a good place to be. So
more variety.
Yeah, more variety. You can see
that boing, boing, boing.
Yeah, V1324 SCO. That was a big project, and that a lot of the work on that one was done by a graduate student at MSU named Tom Vinzel.
Okay.
He did a lot of the work on the radio side of that.
Shout out.
So yeah, that one was very strange. You can see it has very definite double or two radio peaks, one early on and one slightly, or one later, like what, 300 days or something like that. And also that the not only that, but the optical did some weird stuff as well. Like it basically went all the way down to almost non-detections and then kind of bounced back up again.
Correspondence, yes, yes.
So, like I said, there's no such thing as a typical nova. You never know what these things are going to do.
My bad.
One that I would, another one I'd like to call out is V959 Mon. That's in the upper right there.
Oh, yes.
We don't have a pretty picture of this one, but if you look up V959 Mon, that's our poster child for our modern understanding of what's happening inside classical nova.
Okay.
You see the radio light curve looks typical-ish. It does have a funny thing at the very early on there where you see that early blue point above the black point. That was unexpected, but that's not the only unexpected thing about this nova, I should say. After that, it kind of follows your, predicted, I should say, maybe not typical, but predicted nova radio light curve. You can see the optical curve, was fairly bland. It just kind of started off bright and it got dim. Nothing super exciting.
Yeah. No outbreak.
But V959 Mon also has a special place in my heart because it's the first one that I really worked on when I started working with Laura.
Oh.
So
yay.
when I started as a postdoc working for her several years ago, that was one of the first ones I got to play with. It was a lot.
Oh, very cool.
Yep. But that one, we actually had resolved images with the VLA. So when it was in the A configuration I mentioned earlier, where the antennas are really far apart, we were actually able to resolve the thermal emission from this thing into two distinct lobes moving out from each other.
Mm-hmm.
But at the same time, we got very long baseline array, so VLBA observations of it, and we're able to detect non-thermal emission inside that thermal emission. So this was one of our first hints, like Elias was talking about, of where these shocks are forming in these.
That's
so
the structure. Okay.
Yeah.
Very cool.
Another one that was a real head scratcher is V339 Del. That was like the second one or third one I think I worked on. You can see the optical light curve has some structure in it. It's not super exciting, but an important thing about V339 Del is that it was detected by the Fermi Gamma Ray Telescope fairly strongly. It was a fairly bright gamma ray source for a fairly long time. And we got really excited about that. And you can see all of our non-detections up early in the radio there.
Mm-hmm.
We kept looking at it and waiting for it to be a detection. And finally it got bright. And then it just kind of settled and almost plateaued. You can see it stays, especially at the 4.6 gigahertz, those black data points.
Mm-hmm.
It just kind of stayed kind of bright, moderately bright, not super bright, before finally rising again. And then basically
boom,
just falling off. So this one, yeah, the structure in the radial light curve on this one was very puzzling, but it's not, as just, as we go on, you'll see it's not the only one that's very puzzling, but
almost a mini dust formation here, if the same analogy holds.
I can't remember. Elias, do you remember if that was a dust?
Likely, it's a weird dip, but it's likely not a dust dip. Usually dust dips like last longer and they are like shallower. This one, like deeper. This one is quite shallow.
This one's shallow.
Yeah, shallow.
Compared to the other one.
Compared to other ones. So if you look at for example, if you go up a little bit just to look at V1324, let's go the same plot. Just no, I meant the same plot. And then
back down on figure 2.
Yeah.
Figure 2.
No, not figure 2. Figure.
3. Sorry.
The one that we're looking at.
Yeah, figure 3.
3.
No, you're comparing it to the relative dip of, like, let's say this.
For example, let's say this.
Right, you were saying this is the dust, right?
Right, this is for sure a dust. Like, if you
longer, deeper.
Right. Compared to, for example, what we just saw now, it was much shallower and
right.
Yeah. So likely it's just like some dip in the light curve for some reason that we don't know. I mean, we see, as I said, we see. Yeah. I mean, if you just go a little bit higher in this same plot in figure 3, we can see, for example, the top left one is you see how this is a dust dip. Like this is a proper dust dip, and you can see it went like 8 magnitude like down. One thing about V959 which also has been very interesting, is that if you look at the optical light curve, it started like, I don't know, 30 days or 40 days. That's the top right one, and usually we discover Novae in the optical. However, this one is maybe the only one that has been discovered in gamma ray first,
right?
Because so it was in solar conjunction, and we cannot see it in the optical, but Fermi could look at it. So Fermi discovered it in the gamma rays before we discovered it in the optical, and that was I'm saying we actually probably was still in undergrads, but yeah, I mean the community discovered it in the gamma rays first, and then in the optical, and that's why the optical light curve even like starts after the radial light curve, which is you can see on the plot here.
Yeah, fun thing about radio telescopes, we don't really care where the sun is. Well, we care, but not as much.
Not as much. That's a fair way to put it. Okay, very cool. Where shall we go from here?
I think.
Do you want to say about the early peak in the synchrotron emission?
I was going to get to that a little bit later.
Okay.
Fine, let's see.
Figure 4 is more variety.
Yep.
More bounces.
More variety. Things
More
bounce
variety.
around.
5 is more variety. Look
And
at
a nice dust dip on V705 cast there.
So Elias, in figure 5 here, is this a proper dust dip?
Yeah, this is
Thank you.
quite
I have-
That's what, it's like 10
Citizen
magnitudes.
science here. I can identify a dust dip now. Okay.
And you can see that there's a recovery always after it. So the dust is destroyed and there's a recovery, and you can see that then the optical brightness picks up again.
Yes.
Yeah.
Okay. I'm good. Okay. Figure 5. Very good. Figure 6. We have more variety. Okay. A little less data in some of these.
Mm-hmm.
Some of these don't have a lot of data, optical or otherwise.
True.
Okay, figure 7. You have 17 figures here.
Now I'm trying to remember all the details of all the ones that I actually worked on.
That's okay. We'll just keep sliding through. If one triggers a synapse, you fire. Okay.
And
Oh, yeah, that looks like a dust dip to me. I'm well trained now.
Right. Exactly. And one thing is that, for example, in this example or many other examples, we see like these flares or like optical light curve, and we've seen many of them. And this is, I mean, there were many suggestions for what is causing these type of jitters or flares we see in the optical light curves, and some were that suggested that maybe the photosphere of the white dwarf is probably oscillating for some reason. Some have suggested the new episode of mass ejections. The thing is that these flares were like different in different novae. So some of them like would last for a month and go down, then another month. And some of them would go up in 2 days and come back. And like some of them would go for 2 magnitude or 3 magnitude. And some of them is just like half a magnitude. So what all this variety of flares we see in the optical light curve of novae. And we were very lucky actually with a nova that is in this paper actually. If we go to figure 9.
Figure 9.
So it's called V90. Yeah, this figure 9. It's called
figure 9.
9. Yeah.
there we go.
Yeah, so this figure. So this nova on the bottom left, V906 Carina, it's from 2018. And the optical light curve here from the AVSO is not very special. It looks like there is some like plateau at the beginning, and then there is a dust dip, which lasted a bit. But what happened with this nova is that we were very lucky that one of the CubeSats from the Bright mission, it's a Canadian, Polish, and Austrian mission. Now called Bright Nanosatellites, 6 CubeSats that they were launched to monitor giant or bright stars. And one of them was monitoring a bright star in the constellation of Carinae when the nova erupted in the same field, very close to this bright star. And the satellite recorded the eruption in real time with immaculate resolution. So we got this nice light curve following the eruption from its start, and then at this peak in the plateau and the peak, it showed these flares that lasted for just a couple of days. Here they are not very clear because this is not the bright light curve, this is the AVSO light curve. And but you can see some dots, for example, around day 20 or something, where like there are some jumps in the optical light curve. Yeah, exactly these ones. And we're like, oh, whoa, I mean, we are used to seeing jitters and flares in the optical light curves of Novae, so that's nice. But this nova was bright. It peaked at like 6 magnitudes. So we're wondering what happened was like Fermi did detect it in gamma rays. Unfortunately, in the first 2 weeks of the or maybe even for 3 weeks of the eruption, Fermi went offline due to issues with its solar panels.
Yeah.
So we're like,
Okay.
okay, well, damn it. And then when it came back online and started working again, it detected very bright GeV emission from V906 scar, and it was like the brightest we detect from a nova. And not only that, we detect emission, but actually we managed to build a light curve. And the gamma ray light curve showed the same flares that were happening with the optical at the same time.
Very
So
good.
we have flares in the gamma rays and flares in the optical.
Yeah.
And we put these two together, we're like, an aha moment, because we know for sure that the gamma rays are coming from shocks. And I mean, they should be. And if the optical flares or these jitters are also happening at the same time as the gamma ray jitters, that means they should share the same origin. I mean, I know correlation doesn't necessarily mean causation, but there's no reason for them to happen at the same time unless they share the same origin. So it was for the first time we have like smoking gun evidence that a large fraction of the optical emission of a nova could indeed come from shocks, because during these flares, the luminosity of the nova was doubling at least, because they're like a magnitude and amplitude. So it was for the first time smoking gun evidence that, hey, shocks could indeed power a large fraction of the relative luminosity or the optical luminosity of a nova. And V9, so we have now like 2 Rosetta Stones, and I think in the field of nova, V9591, which is beautiful radio images of these 2 colliding flows. And we have the gamma ray and optical high resolution light curves of V906 scar, which also highlight the important role of shocks in Novae.
Very cool.
Yeah. And I have to mention that the radio light, so V906 scar is at, I think, declination -60, I can't remember, but it was 2 stars for VLA. So the radio light curves here, for example, are from ATCA, the Australian
Australian Telescope Compact Array.
Compact array, yeah.
Yep.
So we have a few observations actually in this paper that are obtained with ATCA, radio observations that were obtained by ATCA, particularly for novae that are 2 stars for the reach of VLA.
Big thanks to our Australian collaborators for that,
right.
by the way. We appreciate it.
Shout out. Here we go.
If you scroll up slightly, there's something on there you go, in V357 Muskie at the upper right there. There's a rather impressive dust dip, which also corresponds with this first radio peak temporally.
Yes, it does.
So,
yep.
So as I start talking a little bit more, so I've been kind of vague about what these first radio peaks are and the second radio peaks are. As we get down the paper a little bit, I'll start calling more attention to that and explaining what we think is going on. And Muskie ends up being possibly a third poster child. Remains to be seen. Poster child. For one more really cool thing in Novae.
Very nice. Good. Well, we should maybe head down to one of those. Want to go down to one of those figs?
Let's see.
Slide down a little bit. Figure 10, flux densities. Figure 11.
Right. So, yep. These ones are basically showing you more or less what we expect to see. Naively, you would expect that if the emission, is radio emission and the optical emission are related, or at least if the peak, if what determines the peak is set by something similar in both cases, you would expect them, right, to have a correlation. And that's what we see here, in that the optical peak and the radio peaks are roughly correlated, right? So if it gets really bright in the optical, it tends to get really bright in the radio.
Yes. Okay.
Similarly, with the time the time from maximum to fade 2 magnitudes, the T2, and the time the total duration the time to maximum in radio should also be related, right? It's all one expanding flow. It should be related. It appears to be. And the expansion velocity, if it's moving faster, then it should dim sooner, which is, again, what you see.
Right.
So all right.
It's a physical system.
Yep. So that makes sense. Here is where we're going to start getting into some more of the physics. And one thing I want to draw your attention to is that equation number 1 right below the figure there.
Okay,
so this is the equation for something in radio astronomy called a brightness temperature. The idea here is this is the physical temperature that something would have if all of the emission was coming from thermal processes. So, if everything is that bright because it's hot, then you can tell how hot it is, just based on this. Ideally, you want it to be a resolved radio image so that you have a good sense for how big the structure is. But in case with Novae, you can't always get that. A lot of the times, especially early on, they're far too small to be resolved. They're just point sources in your radio images. So you have to rely on things like the distance to them, how long they've been, how long it's been since they've erupted, and how fast the ejecta is moving. So this is where we rely on things like Gaia to give us a good distance, on optical spectra, like Elias was talking about, to get us the expansion velocities and that kind of stuff. What you see there then in figure 12 is we have on the right-hand side, you see the brightness temperature versus time for several of these nova. In this particular one, these are the fastest 7 novae, so the ones that evolved the quickest.
Okay.
For us. And you can see there, we have a line drawn, that dotted line at about, was it 5 × 10⁴ Kelvin?
Okay.
That is roughly the limit that you would expect for thermal emission in a nova.
Okay.
There's a few reasons for that, that the details are in the paper, but for now, just kind of accept that it can't really be hotter than that if it's all thermal emission. Anything that you see with a brightness temperature higher than roughly 5 × 10⁴ Kelvin pretty much has to be non-thermal emission. So this is where we're talking about synchrotron. So once again, we get to these relativistic electrons that shouldn't be there, right? So we're delving into the shock idea again. So we know these things produce gamma rays from shocks. We also have synchrotron, radio synchrotron emission is probably coming from shocks. Hopefully it's coming from the same shock. Otherwise it's going to get really complicated.
Well, yes. Yeah, it does simplify things if there's only one.
But so you can see here, there's a few objects in here, in particular V392 Per and V838 Hercules, that are very obviously above this 5 × 10⁴. In fact, they're in like, the 10⁶ regime. That has to be non-thermal emission. And notice that a lot of times with these, the non-thermal emission, the strong evidence for it comes early. So in those light curves that I was talking about earlier, where you see 2 peaks, right? You see the first peak, we're pretty sure that's non-thermal, or at least has a large contribution of non-thermal emission. It also tends to correspond roughly, not exactly, but roughly to the time that we're getting the gamma rays. So we know that there's shocks from gamma rays. We now have non-thermal emission from synchrotron or in the radio. So that explains that, if you've got a shock early on, you're going to accelerate these particles. They're going to emit non-thermally. You get this early radio flare.
Makes sense.
And you can see that at least for some of these, like there's 3 major ones in this. So V392 Per, V5589 Sagittarius, and V838 Her. It's pretty unambiguous that these are non-thermal. The other ones, there could be non-thermal in there, but you can also kind of hand wave and say it could just be thermal. It could be a mix. It's a little bit unclear on that. But a few of these are very clearly non-thermal emission.
Yes. The peakiest of the peaks.
Yes. So now if we head down to figures 13 and 14,
Okay.
this is the same idea again. So you've got on the right-hand side there, you've got the brightness, temperature versus time. And again, you've got very clear candidates where especially check out V357 Muskie, the blue one with that really sharp peak.
Yeah.
Okay. So now I'm going to ask you to bounce back to the light curve for that one.
Okay.
That's in figure 9. Right there. You passed it. There you okay.
Getting there, getting there.
Getting there. A little more.
Sorry, 9.
There we go.
Yes.
Okay. So you can see where we see that strong synchrotron is that first radio flare, which also happens to correspond to that dust dip.
Okay.
So now we have 3 things all lining up. We've got non-thermal synchrotron emission, we've got shocks, and we have a dust dip.
Awesome.
This makes us think that a lot of the times, especially, and Muskie was also a gamma ray detectanova, I'll point out. So we know there's other non-thermal emission going on there. It's hard to imagine dust forming in this kind of environment, right? You have all this hot, fast moving material, but if you form a shock, then you can shield it. You can shield some of that material, you can cool it down, and it can condense.
Okay.
So that's why I said now Muskie might be our 3rd poster child.
Very nice. Very cool.
So some very interesting physics that you can tease out of these things by combining, especially doing multi-wavelength observations of these novae. You wouldn't find this stuff with just looking in the radio or just looking in the gamma rays or just looking in the optical.
Right.
Putting all of them together, all of a sudden you start finding cool stuff.
Very nice. Very nice.
And I wanted to point out to some theoretical work by our theoretical friends, particularly in Columbia, a group with Brian Metzger and his group, who does a lot of theory on the ethical side of the work on Novae, and they like motivated by these observations that we get across the spectrum. They try to test theoretically if shocks could indeed form ideal environments for dust formations, and they try to get an idea to estimate the temperature of the gas in the post-shock region and see if it's cool enough for dust to condensate. And that's one of now the current theories for dust formation, is that, as Justin mentioned, they could form in post-shocked regions within the nova ejecta. Because previously, well, we didn't have a good idea about how dust forms, but people thought that there were some clumps within the ejecta. The ejecta of novae tend to be clumpy, so these clumps could form ideal environments to shield the gas from the dust from the irradiation from the hot white dwarf at the center, and therefore could allow for dust formation. But now we have this like very new idea of shocks being the location to shield the dust and allow it to condensate, which I think it's a really, really cool idea. And as Justin said, the only way to figure this out is by putting all the pieces together and putting like the observations from across the spectrum.
Nice.
It has been absolutely fantastic working with Brian.
Right.
There's a shout out. Yeah,
yep.
Brian. Very good. Okay, and then I think the remaining 3 are the same for different sets of any particular call outs here you want to do?
Nothing in particular. All these ones are more or less, they look kind of thermal. There's maybe some where they kind of start sticking up above that cutoff, but for the most part, it's hard to make any argument that there's anything non-thermal.
Okay, very cool.
It's possible, but it's harder.
Okay.
So,
all right.
Wrapping up the radio observations on this is that we've seen multiple examples of these novae that have two radio maxima, an early one that seems to be driven, or at least have a heavy contribution from non-thermal synchrotron emission, and a second peak later on that tends to be fairly easily explained by just regular thermal free emission. We've seen that that in certain cases, that non-thermal emission happens to line up very well temporally with dust emission. We've seen that a lot of the novae that we see this non-thermal emission in also happen to be detected by the Gamma Ray telescope, the Fermi Gamma Ray Space Telescope. So there's a lot of cool stuff you can do in novae. No matter what your favorite wavelength is, there's cool things you can do.
Oh yeah, well, it's all telling a consistent story, so that's nice. It's always good. Okay, little shout out to Bob there at the end.
Oh yes, yeah, he did a lot of pioneering work on the VLA, observing novae. A lot of those early archival things where he did a lot of work on those.
Very cool. Good. All right. Well, Justin, Elias, thank you so much for walking us through your very lovely APJ sub-article.
Thank you.
Thank you.
And you touched on it a couple of times throughout. But nevertheless, I want to follow it up a little bit. So where do we go from here? Let's say over the next 2 to 5 years. Is there going to be some new observations coming at any wavelength, apparently? Right, does JWST, VRO, etc. do any of those come in? Is there other additional theoretical work that could be done? Why stop with 2 shocks? Why not go with 4 shocks? And then intersect the shocks just for extra fun. And just sort of like where do we go over the next couple of years with classical novae in radio?
The next couple of years, I think our team is very curious about this connection between the dust formation and the shocks. We have some ongoing observations. I think we have another, I can't remember how many programs we have, but some of the members of our team are working with the Gattini IR people that monitor the sky or do transient follow-up in the infrared. So we could get some more information about dust formation from that. I know Elias is leading some cool projects, right?
Yeah, so
tell me a cool project.
Right, so yeah, we're trying to confirm this theory of the connection between dust and shocks by, as usual, combining observations from different wavelengths, but also different type of observations. So we have some cool project now that we are planning to execute is by combining imaging with spectroscopy. To try to confirm any link between dust and shocks. So recently we have been working hard on trying to image novae from the beginning with facilities like CHARA. So CHARA interferometry can resolve the ejecta in the early days or early hours of the eruption. So usually with like facilities like the VLA or VLBA or even ALMA, for example, we only image the ejecta when it's expanded enough, like maybe a few months or a few years after the eruption. But with CHARA, we are able to track the evolution of the ejecta, the way they are shaped and the way they are interacting in the early days of the eruption. And we have now some cool examples of seeing these two autoflows in the early days of the eruption. And we're going to try to connect it later on with the VLA radio observations and see if this structure has been evolving with time, how it is evolving, where are the synchrotron emission from the VLBI observations located, and then try to even, if a nova, for example, formed dust, try to check, for example, in the millimeter, if there's any excess of emission in the millimeter from dust, try to see if it's indeed at the location of the synchrotron emission at the interface of these two autoflows to try to come up with a connection between the dust and the shocks. And also with spectroscopy, you'll be able to get an idea about the velocities, which would, sorry, you wanted to say something. Yeah, go ahead.
I'm just,
Yeah, right. So another way maybe to test this theory is from spectroscopy, where like we measure the velocities from the optical lines, where the optical emission should be coming from everywhere, so it would reflect a wide range of velocities throughout the ejecta, over all the way to thousands of kilometers per second. However, for example, dust tracers like CO lines and the infrared, if they are indeed coming from this like equatorially confined chalked regions, which have velocities of a few hundred kilometers per second, means that if we observe a nova during a dust dip in the optical and infrared simultaneously, we should see optical lines with a few thousand kilometers per second velocities, but infrared lines with a few hundred kilometers per second velocities. And if that's the case, it means that the infrared emission or the CO emission or the dust is coming from equatorially confined.
Okay,
so
cool.
This is one of the projects, yeah.
Cool. It's going to be really fun to watch this develop over the next, let's say, 5 years or so, as a number of these new facilities come on, and we'll start twisting down on classical novae.
And you mentioned the next 2-3 years, but there's something really interesting about novae that we haven't touched base on, is that, first of all, we're barely scratching the surface of understanding shocks in novae now, and there's still a lot to understand. But given that novae are potential cosmic ray accelerators, we might expect maybe to detect neutrino from novae. And so far, we haven't detected any with facilities like IceCube. But if we go, for example, to lower energies, facilities that could detect neutrinos, not the high energy TeV neutrino maybe, but like at lower energy neutrinos, we might be able to start detecting neutrinos from novae. And then we have a new class of neutrino emitters just in our galactic backyard, and imagine all the implications and all the physics we can study using these very nearby objects.
Very cool. Nice. Yes, I like neutrino detections. Very cool.
I'd say one other thing that I'm excited about in particular, and it's looking longer than 5 years, but it's still the next generation BLA. Having basically better than A configuration radio imaging for every single data point in a light curve, right? So instead of just getting a point source every time, you're getting result images, and those light curves basically turn into movies. You can watch the ejecta expand and change and evolve. That's going to be really exciting.
Awesome. Yep. Yeah, that is a little longer time scale, but it's within the causal horizon. Let's put it that way. You'll be able, it's there. Very good. All righty, Justin, Elias, thank you so much for walking us through your very lovely article.
Thank you for having us.
Well, thank you
so much.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye-bye.